Hello everyone, my name is Jafari and I would like to welcome you to another video. In this video we're going to answer the obvious question. So we did the clustering and we have the outcome. How do we know if it's any good? Alright, let's look at the slide. So to be able to answer if we know and how we go about knowing if our clustering is good, we are going to first understand the difference between how we would evaluate clustering, how we would evaluate classification and prediction, and how it's different than clustering. And then we'll talk about two ways of going about this evaluation. We call them extrinsic and intrinsic, and we'll see that why extrinsic evaluations is not applicable most of the time. And we will learn about two methods that we can use for intrinsic evaluation. We will learn about their uniqueness and their advantages and disadvantages. And of course, we'll wrap up the video with a summary. All right, if you remember, when we do classification or prediction, our goal is to find the patterns that connect the independent attributes to a dependent attribute so we can use this pattern for the task of prediction or classification. Of course, the difference between prediction and classification was simple. For prediction, our independent attribute were numerical, was number. For classification, it was categorical. It doesn't matter really as far as how we would, so fundamentally we would go about evaluating classification and prediction. At the end of the day, we would come to a prediction and we would also have the actual for the test set, right? And by sort of like finding the similarity between the actual and the prediction, we could, have some sense of how well our algorithm were doing or how well we did the task of prediction or classification. And of course, we had different metrics. These metrics had different, personality, different, uniqueness. We had to know them, but that is beside the point. The point here is that we do have something to compare our performance with, and that is not the same as clustering. When we do clustering, we basically group our data objects based on the inherent similarity between the data objects based on the attributes, right? So this is what we do for clustering, right? And in the past previous videos, we learned that when we have these clusterings, we can sort of like compare them to see how similar these clusterings are. And we did see in the previous video that when we have this capability to compare clustering outcomes, we can use it to see if a data set is clusterable, or there is clustering tendency, or there are inherent clusters in the data set. But here we're going to take one more step and we say, okay, we do have this clustering, and this clustering is coming up the same again and again, and we do have this consistency, which in itself is an indicator of the high quality of clustering. If there were no clustering, if there were no patterns in your data, you wouldn't have the clusters. So in itself, it's an indication of you having reached a meaningful cluster. But it doesn't serve as the purpose of being able to say, okay, which algorithm is doing better, or which one of these outcomes I want to use. And it doesn't answer those questions. So now what we're going to do is be able to sort of like answer those questions. So there are two approaches, two ways to look at this. You don't have the luxury of being able to use both of them. If you can use the extrinsic one, it's actually great, right? With the extrinsic way of seeing how well your clustering has done is basically only possible when you have a ground truth. You actually know what are the groups that your data objects should have sort of come to. And that's a very unrealistic expectation to have from your decision-making environment. If you knew the groups while you're doing clustering. And you may have done your clustering, you may have chosen a wrong task, but there are very few cases you actually need to do clusterings and actually you've got the ground truth. But rarely do we have that luxury. Most of the time we have to rely on the intrinsic ones, and basically we have to find a metric that, based on the outcome itself and of course the data objects and how close they are with one another, to come to a metric that gives us some sense how good this outcome is and how good is the other outcome, so we can compare them to one another. So a few words on the extrinsic one. If, let's say, in rare cases, if we do have those those ground truth, which is very rare, how do we go about this sort of evaluation? And the answer is very simple. I mean, you've got the ground truth, you've got the clusters that are correct, and then you've got your clustering that you've already done. How do we know if it's any good? It's very simple. You see how similar this clustering that you've done with the ground truth is, and the more similar the better. And the similarity metrics that we already saw in the previous video, not the previous, the one before that, comparing clusterings, could be Rand's, Wallace, Folks-Mallow, and J-Cars and H-criterion. And of course we sort of talked about the uniqueness, the advantages of these. So you want to choose one of these to compare the ground truth with the clustering you've done. So for the rest of this video, we're going to talk about intrinsic ones, and specifically we're going to learn two intrinsic metric that we can use to evaluate clustering. The first one is sum of a squared error. We've already talked about this a little bit when we were learning about hierarchical clustering, but let's learn it one more time. Basically, the best way to think about sum of a squared error is to sort of think that by clustering your data, let's say you don't want to deal with all of the data objects you already have, right? You want to throw out all of the other attributes, right? You've got data objects. From now on, all you're going to look at are going to be this cluster, right? So the data, the attributes you have, you're going to just discard them. And from now on, you're going to have this just one column. It's basically a new column, right? So sum of squared error basically calculates the loss of information. How much information are you losing if you were to discard everything else but keep this cluster? And the way it goes about it, it basically calculates the centroid of each of these clusters that you've come up with, and calculate the distance of each of the data objects from the centroid of the cluster that data object is a member of, right? So that's basically it. It calculates that and it uses that to say, okay, which clustering is better. So let's look at an example. So for example, here the SSE would be the centroid would be something here, centroid would be here. So the distance between all of these data objects, all right? So all of these, no, not this one. And all of these, the summation of all of these distances, right? The summation of all of these lines, however long they are, would be the SSE here. And pay attention here in the next slide, the same data, but here what I have is I have 4 clusters, right? Basically, this one larger cluster has been split into 2. Pay attention, right? So now I have to calculate another. So I've got 4 clusters, right? And when I calculate all of these distances, now it will be my new SSD. So by looking at this example, you can see that why it is that if we have more clusters, our SSE seems to be smaller, right? The more clusters we have, the SSE is smaller. So, and there's a very unique feature and characteristic of SSE. That was the reason when we were using SSE to find the best number of clusters using k-means, we were using the elbow method. Basically, because SSE, every time we have a more number of clusters, we expect SSE to actually improve, or the value of SSE to decrease then the way we go about using SSE to find the best number of cluster is to say, okay, if the rate of improvement decreases when you jump from a cluster, a number of clusters, to the next one, then that could be a kind of an indicator for us that maybe this is the best number of clusters. And of course, this is not this is not a characteristic that all of the other metrics, the one that we're actually going to see, silhouette coefficient, also have. So let's just start talking about the silhouette coefficient. With silhouette coefficient, we have a metric that is more complex and more capable than SSE. The silhouette coefficient not only does capture the compactness of the clusters, something that SSE was also doing, but also captures how far and how dispersed these clusters are from one another. Another difference between SSE and the silhouette coefficient is very important for you to understand. SSE is a number for all of the clusterings. For one cluster, you come to one SSE, sum of squared errors. With silhouette coefficient, every data object within this clustering will have this coefficient. And you have to calculate A and B for each of these data objects. Essentially, A is how compact the clustering that this object is a part of, each data object is a part of. And B is how well separated the cluster that this data object is part of from the other clusters, right? So basically, like I said, A is that compactness, and because it calculates the distance, the lower the A, the better is the clustering. And for B is to the degree that the cluster that they're always part of is separate from the rest of the cluster, and the higher the B is better. So basically, the higher silhouette coefficient you have, the better clusterings that this data object is a part of. So how do we come to one number, right? I mean, every data object has one silhouette coefficient. How do we come to just one number so we can evaluate the whole clustering? And the easiest way to go about this is to do an average of all of the silhouette coefficients of all of your data objects, and that gives you one number that can be compared with the another clustering silhouette, which is the average of the silhouette score of all of the data objects for the same data set. And of course, the higher the silhouette, the better. Alright, so in this video, we talked about the evaluation of clusterings, and we did see how evaluating clustering is different than evaluating classification and prediction, and we saw why is that. We also talked about why is evaluating clustering is important, and we did see two approaches. Extrinsic one, we did see not all of the time we can actually use the extrinsic one, and we have to rely on the intrinsic metrics, and we learned about two specific metrics for the intrinsic evaluation of clustering. We see there, we saw SSE and silhouette score. We saw their capabilities, their uniqueness, and their advantages and disadvantages.